All right, ladies and gentlemen, welcome to Chapter 2 of Biology. This chapter, we are going to be talking about the chemical basis of life, which means the chemistry of keeping you alive. And we are going to care about two basic things, food and water. And that is the whole basis of this whole chapter. And specifically, the weird things about water that keep you alive. And water is weird. And you're just used to it, so you don't realize. And with food, four major molecules that you need to stay alive. We call them the macromolecules. So let's jump into the vocabulary and get started. All right, so chapter 2, the chemical basis of life, vocabulary. First half of this will be about water, second half will be about food. So your first word dealing with water is cohesion, an intermolecular attraction between like molecules. That is your keystone definition. I don't personally like it. I like to say water sticking to water. It doesn't actually have to be water, just what we're focusing on. Anything sticking to itself. So in this case, syrup sticking to syrup, water sticking to water. Right? That's cohesion. And syrup, you can see, is more cohesive than water is, because that's why it's not dripping off, not just falling off this honeycomb. It's being pulled because it's not letting go of itself. Over here, it's getting pulled, but eventually the water does let go and becomes drops. So this is more cohesive. But water is still very cohesive. Not to be confused with adhesion, an intermolecular attraction between unlike molecules, which means water sticking to other things, right? One substance sticking to another substance. That's what it means to adhere. Right? Tape, glue, Band-Aids, these are all known as adhesives. Right? Band-Aids are actually known as adhesive strips. Now, so to adhere or adhesion is to stick to something else. Water sticking to a spider web, water sticking to the pine needles of a pine tree. You get the idea. Capillary action. The tendency of water to rise up a thin tube. You're actually using cohesion and adhesion in this. All right. So water is adhesive, so it sticks to the inside of a tube and starts climbing up the top. And because it's cohesive, water sticks to itself, the water down here is going to hold on to the water here as it's climbing, and it's going to get pulled up with it. So why are these words important? Why is cohesion and adhesion making capillary action happen? Why is that important? Because plants, right? They can't just suck water up through their roots. They don't have the ability. They don't have any kind of muscle to do that. Water is going to ride itself up a flower's stem to the top. You can see in this picture here, half in the red water is bringing red water to the top, and this half of the flower turns reddish pink. Where this side is clear, so this side of the flower stayed white. So plants are going to be getting something to drink through this, and no plants, and that's important because we need plants to survive. No plants, no humans. pH, the measure of an acid or a base ranging from 0, which is an acid, to 14, which is a base, or alkaline. 7 is right in the middle. That's water, neutral. So to really understand this, a little historical context helps a bit. This gentleman is Soren Sorensen. Not sure if I pronounced that right, but he was a scientist who worked in a laboratory funded by a beer company. So he was working on making better beers. He found out that the amount of hydrogen in the chemicals he was using actually mattered when making these liquids. So he lined them up from the most amount of hydrogen to the least amount of hydrogen. And what he found was the stuff with the most amount of hydrogen ended up being the most acidic. And the stuff with the least amount of hydrogen ended up being the most basic or alkaline. And I didn't get those numbers mixed up. Yeah. The lower numbers have the most hydrogen, the higher numbers have the least hydrogen. What else he discovered was when he lined them up and numbered them, that each number was actually 10 times more powerful than the previous number, meaning 7 is neutral, that's water, we can drink that. 6 is a very weak acid. 5 is 10 times more powerful than a 6. And 4 is 10 times more powerful than a 5, and so on and so forth. And then other way around with the bases, an 8 is a very weak base, and then a 9 is 10 times more powerful than that. A 10 is 10 times more powerful than a 9. You get the idea. And what we're going to talk about is that the acids can cancel out a base. That's very important for our next word. So, I mean, if we took a 6 and an 8 and mixed them together, long as you got the measurements right, you can turn them into a 7. They can cancel each other out and become water. Same thing with a 5 and a 9, mix them together. If you get the measurements right, you can turn it into a 7. So with that in mind, a buffer, scroll up a bit, a weak acid or base that can react with a strong acid or base to help prevent sharp, sudden changes in pH. Right? Basically, a buffer will mellow out something, right? Water it down. So if I have a strong acid spill, hydrochloric acid, I spill it on the floor and I don't want anyone to get hurt, I would take a weak base like baking soda and just keep pouring it onto this acid a little bit at a time. You probably learned in chemistry class, never mix an acid and a base, right? Hydrochloric acid and drain cleaner mixed together can be very dangerous. But if you take a weak base and mix that with a strong acid, it will actually cancel it out gently, and it won't be that dangerous. And you just keep adding and adding and adding until it's completely canceled out, and you're good to go. So this will just keep watering it down. Why is this a property of water? Because water is the universal buffer. I can keep adding water to hydrochloric acid, or I can keep adding water to drain cleaner. And either way, it'll cancel it out. You just need a lot of it. All right, so that's it for water. We'll talk more about that in the next set of notes. For now, let's move on to the molecules in the food that you eat. Right? And we are focusing on the molecules, not the actual food itself, right? Molecules in the food. Our first word is monomer, a molecule with carbon in it. It can react with other monomers to make a polymer. All right, so let's break that down. First off, what is a polymer? It's our next vocab word, right? It's just a large molecule made up of monomers, right? So monomers, any food molecule really that has carbon in it, right? That's a very important atom that we care deeply about, and we will talk about in a future set of notes. But all of your food has carbon involved. You take these molecules with carbon and you put them all together and you get a polymer, which is the molecules that we really care about in your food. So small molecule, big molecule. And then macromolecule. This is a polymer, all right? This isn't the next level up. This isn't like a bunch of polymers together. This is one polymer. It's just a very big polymer and a very important polymer. This is so important, these macromolecules, that there's only 4 in existence and we cannot survive without them, right? The polymer with a high molecular mass. Our 4 macromolecules are carbohydrates, proteins, lipids, and I skipped one here, nucleic acids. I'm saving for a different chapter. All right, so we'll talk about 3 of the 4. Carbohydrate is a macromolecule that carries energy into your body. You probably heard of carbs, right? If you're ever on like any kind of diet plan, the main thing is to cut out high carb foods like bread or potato chips or pasta, right? These have a tremendous amount of energy. The reason why it helps you lose weight to cut them out is because your fat is just storage. You have a lot of carbs, energy stored in your fat. So if you cut out your energy molecules, you need to dip into your fat storage for that energy. Our next macromolecule is proteins, the macromolecule that is used to build up your body. Things like meat have proteins in it. Your body is made up of proteins, and those proteins you get from the food you eat. So the more you eat, the more body you can have. So carbs give you energy, proteins give you material to use to build up yourself. Right? These are basically the Lego pieces that build up your body. And then lipids, the macromolecule that is used for storage. This is what your fat is made out of. I said your fat is storing extra carbs. If you eat a lot of carbohydrates and you eat a lot of proteins and you don't need that much, you're going to end up storing it in your lipids. And that's how you build up your fat molecules. And there are good lipids and bad lipids, good fats and bad fats. Rule of thumb, if it is liquid at room temperature, it is a healthy fat, a healthy lipid. If it can stay solid at room temperature, it's probably not healthy. So healthy things, not healthy things. Enzyme, a protein that increases the rate of a chemical reaction without being changed by the reaction. Again, another keystone definition. All right, guys, remember, this is the chemical basis of life. We are talking about chemistry, and with chemistry comes chemical reactions, meaning two molecules are going to come together, two chemicals are going to come together, and they're going to do something. An enzyme is just a molecule that's going to help those things come together. It's a tool, right? It's not actually involved in the chemical reaction. It's not changing anything. It's not being changed. It's just going to get the right things into the right place. If you look at this picture, this is your enzyme, and this is the substrate, the chemical that's going into the reaction. And notice that it's going to fit perfectly like a puzzle piece. So only these chemicals can go into this enzyme. It's the only thing it does. And it is going to make sure that it's in the right place at the right time in order to break apart. Enzymes are just there to make it happen. But by the end of it, the enzyme is unchanged. Throughout the whole process, the enzyme looks exactly the same. So you can keep reusing it. And your last one, activation energy. This is a term you've probably learned in chemistry class if you took that already. This is probably a term you've learned in physical science. Activation energy is the energy required to start a chemical reaction, to make it go. So this graph shows energy involved. Nothing's really happening. This is just the energy in the reactants. This amount of energy isn't making anything happen. And then suddenly, we want something to happen. So your body has to increase the energy. You got to put your own energy into making the chemical reaction happen, and then suddenly something happens. Right? The chemicals get ripped apart, they get put together, something happens, and then once that goes, everything becomes easier. Your body is using less energy until chemistry is done. These are your vocab words for this chapter. We're going to be focusing a whole lot on water in the beginning, their next set of notes. So make sure that you are equipped with those first 5 words before the next video. All right, guys, go on Google Classroom. There should be an assignment waiting for you, and good luck.